Hi, I'm Paul. I'm a third year electronics student, as you may know, and my project is in robust supervised acoustic scene recognition with learning capabilities using deep adaptive neural networks. And I'm basically going to be talking through my project, how progress has been, and basically the problem statement, methodology, and what I found out at the end. So I'll start with the overview. So 2 million people use hearing aids, but actually 6.7 million people could benefit from hearing aids. And so this raises a question, why don't people use hearing aids? And one of the primary reasons why hearing aids aren't used is because people get them and then they put them on and then they realize that actually they don't work very well and they find that they're not very effective. And then secondly, it's the psychosocial factors as well. So it's the social pressures of society. Maybe if you are reaching up to your ear and trying to adjust the hearing aid program in your ear, that might cause a little bit of worry for people, and might make people feel a little bit judged. The fact that they're broadcasting that they're hearing impaired. And so, what does this project address? So it addresses both of these concerns actually by using acoustic scene recognition. And the hope is that this acoustic scene recognition, which recognizes different background noises, can tell a automatic switching hearing aid program the type of background noise that you have. So then you don't need to reach up to your ear and change the program every single time. And hopefully this will improve hearing aid technology in general. Okay, so there's some key considerations that we need to take into account when we're addressing hearing aids. So first, they have to be responsive, so low latency. So you don't want the algorithm to recognize an environmental noise, and then 5 minutes later, then it switches. Secondly, it has to be computationally inexpensive. So hearing aids are quite small devices, and I don't expect the processor on hearing aids to be particularly powerful. And three, it has to be versatile. So it needs to be used in a variety of different situations because people have different hearing, have different levels of hearing. They go into different environments, so you need to make sure that you use a good range of data to solve that. So the responsiveness was addressed by using frame-by-frame analysis. Using simple feature extraction methods made sure that it wasn't too computationally expensive. So there are actually hundreds of features that you can choose from, but I didn't use statistical methods because they were too basic and they weren't very effective. And I also didn't use too complex methods because they would be they'd be computationally expensive. And versatility, use high quality data to make sure you cover enough base so that you can cover enough audio labels so that you can go to a wide variety of environments and not worry about it. So I'll quickly talk about the datasets I use. So I use noisiest dataset, which is speech plus noise, and then it's 2-second samples and 8 different noise types. And also the demand dataset, which is background noise only, 5-minute samples with 6 noise types. So with noises, I only used about a quarter of the data for training, but I used all of the dataset. But the demand dataset was massive, so I only used 2 files per noise type, and then I had plenty of data for testing and training, so that's why it's 50-50 data split. So I'll talk through my methodology a little bit. So first there's the pre-processing. So first I downsampled the signal to 8 kilohertz, and then I split into the different frames, and then each frame is Hamming windowed. So this is the frame-by-frame processing. And we could actually vary the frames. So one thing that I tested was varying the frames from no frames to 100 millisecond frames and 25 millisecond frames. So frames are getting smaller. I kept the Hamming window settings as default. and then each frame is passed into a feature extraction method. So we used 6 different types, as you can see: MFCC, GCCC, gamma tone. I actually found that these had the same underlying um, pipeline, which is why they're very similar, but actually there are subtle differences between them, and which actually made a big difference in the end. Raster, PLP, Gabor, and AMS. So Gabor, I think, highlights textures more. Essentially, every feature extracts different elements of the audio differently. And then you have the classifier. So I used 3 different classifiers: support vector machine, tree, and naive Bayes. So support vector machines kind of essentially draw a hyperplane through your data in an attempt to try and split it. And you can draw multiple of these hyperplanes to categorize multiple data. Tree classifiers are essentially asking true-false questions, and they try and narrow down the data. So say if like a certain value is greater than this, then it basically tries to purify the labels until you get to the end of the tree, and each leaf at the end of the tree is a classified, like, is a label. And naive Bayes uses data to make probabilities of each class, and then uses the model to classify new data. So essentially what a classifier is an optimization program that tries to divide the data efficiently. So how did I test and train this? So as you can see, there are many parameters that I had to sort out, and basically I tested one pipeline. So I use NoFrame, MFCC, and then SVM. And then I would vary the number of, I change the feature and then eliminate the features that weren't performing very well. And then basically every time I eliminated a feature, because it's not possible to test every single thing here. So that's why you have to eliminate features. So for example, one of the first features I eliminated was Gabor, because it just wasn't, the accuracy was just so low. And I just didn't think that it was worth continuing on with it, but I do think that it would be more suitable for image recognition. One very good indicator of how good your classifier is, how well your classifier is doing, are confusion matrices. So down here at the bottom, you can see the blue diagonal of squares, and that tells you how, so the higher the score, the better your classifier is. But you can see here that there's some missing squares for AMS. So it means that it never predicted a particular class for a particular thing. So it can actually highlight a lot of things that you might not notice, because some classifiers, your algorithm might be good at classifying one type of noise. So maybe it's good at identifying train noises, and that's why the accuracy is so high, but it's just not very good at the others. And what we want is a kind of a well-rounded feature extraction method. So after doing all of this and finding out all of the accuracies of the different features, combination of features, frame sizes, and classifiers, I had some quite interesting results that varied quite heavily depending on the data set that I used. So I think it's quite expected that the demand data set, because it's high quality and background noise only, the results were more promising. So here you can see it's in the 70s. But with the noisy data set, because you have that speech added on top, you have so the accuracy is a little bit lower, but not. It's about 10-15% lower. One interesting thing to note is actually the discrepancy in AMS. So with no frame and with 100 millisecond frame, the accuracy of AMS dropped from 70% to 30%, and that was one of the things that I tried to investigate. And actually, And I think I concluded that it probably was because that there wasn't enough data in each frame to sufficiently classify AMS. So you can see at the bottom that there's some separation in AMS with the parallel coordinates plot. So that's the one with the squiggly lines. There's some separation, which is why I think it could have about 70% accuracy. But compared to GTCC, the GTCC, so this is a different type of plot. You can really differentiate between the different labels, and the classifier can easily put a hyperplane through that and not worry about overfitting or overgeneralizing. So the results of the demand dataset seem to be more promising. I'm still waiting on the AMS to train, and I haven't really trained the Cabal because it didn't really have a high accuracy anyway in the first place. So I don't think there would be any point to train it anyway in the first place. So in conclusion, what I found was that GTCC and gamma tone features are the most stable. The quality of the data is very, very important. There's, even though it's a 5% difference between no frame, actually it's easier to compare the 100 millisecond frame. There's a 15% difference between the gamma tone with noises and gamma tone with demand data set. And there needs to be sufficient data in each frame, but this only seems to be a problem with AMS. The gamma tone features, as you can see, is 60.19 for noisiest, and then 60.12 for the 100 millisecond frame by frame. So it's not that much of a difference, and only AMS has dropped significantly. And actually, another thing that we found out is that tree classifiers are just as effective as classifying noise types as support vector machines. So they were also getting about 70% accuracy, but it was training much, much quicker. Same story with naive Bayes, but this is only with MFCC, so it could just be that MFCC is a very good feature extraction method. But I think some credit needs to be given to the fact that tree classifiers are also pretty good as well. Okay, so where is this heading in the future? I think definitely there needs to be more exploration in AMS because that was a feature extraction method that I had to read up on and construct from scratch. And I think there needs to be more investigation on why there is this discrepancy. Even though I explained it a little bit, I think there might be something deeper that's going on with AMS and how it extracts features. Another thing that would be really interesting would be unsupervised learning. So that's basically where you just throw data at a machine, and then the algorithm will actually try and identify patterns. So you don't need to put labels to the data before you put it in the machine. The machine will just try and figure out those labels for you, and then you label them, and then you can classify. So yeah, that'll be something definitely very interesting to try out in future work. So that's it. I hope this was useful. If you have any questions, you'll be emailing me anyway. So yeah, I hope you understood that very clearly, and thank you very much.